welcome everybody. We're going to talk about some radio astronomy stuff here. So here's the agenda. I'm going to give a very brief radio astronomy overview, and then I'm very excited to tell you about telescopes that you can get on your own, buy, use, or build, that are going to be inexpensive. And at the end, I'll spend just a couple of minutes talking about the special interest groups that we're trying to form here in radio astronomy. So the SDAA's mission statement is, we're to further the education of its members and the general public, and then I added an emphasis here, in the subjects of astronomy and related space and physical sciences, and to increase public awareness and enjoyment of these. So I think radio astronomy falls in the category of subjects of astronomy. So let's just dive right in. So obviously light has been around since the creation of the universe, and Maxwell took the work that other people had done and looked at electromagnetic radiation and put together the famous Maxwell's equations. And the reason I'm putting them up here is, it may not be obvious to you, but there is no limitation here on frequency. So electromagnetic radiation isn't limited to the visible light, and this was recognized very early on. And you know, there ought to be electromagnetic emissions at higher and lower frequencies of light, and so, which is in fact true. So this led some people, Nicholas Tesla and Oliver Lodge, that's the Lord Kelvin that we get the Kelvin scale from, to say, well, maybe we ought to look at the sun and see if there was any kind of radio emissions or lower frequency emissions in light there. And they weren't able to find any. And for a long time, I thought that was because their instruments lack sensitivity. It turns out that they were not. We're going to talk about in just a minute, the atmospheric window that allows you to look out. And they were looking at an opaque part. Okay, so the real beginning of radio astronomy was in the early 1930s, and this is just when transcontinental radio communications began to be there. And so people were trying to figure out what was interfering with that. And so Bell Labs hired this Carl Jansky, who was an engineer, to go and try and figure out what all these sources of interference. So some were pretty easy. So in those days, they had unshielded automobile ignition. So he quickly discovered a lot of times when someone fired up their engine, you'd see that. But he built this huge device here at 20 megahertz, and those are Model T wheels, and he turned it around, and he basically aimed so it could go all the way around 360 degrees, so it's an all-paths system. And he was looking for sources of interference, and when he'd find them, he'd try and figure out what they were. But as he published in 1933, he says, the data gives for the coordinates in the region from which the disturbance comes, right ascension of 18 hours and declination of -10. And so this was a source that he couldn't figure out what it was. And so he started timing it, and he noticed that it wasn't every 24 hours did it show up. It was every 24 hours minus 4 minutes, which is, instead of a solar day, it's a sidereal day. And so he realized that that wasn't tied to the Earth, it was actually out in space. And he published his work in 1933, and nobody did anything. And I was shocked, because I thought, how in the world could scientists not have done something with this, until I found out here not too long ago that he was an engineer. He published it in an engineering journal and not in a scientific journal. So engineers looked at it and they're like, yeah, so what, nice. But so along comes the first, and by the way, that's all he did and didn't do any more. So along comes Gort Reaver, who was an engineer. So anyway, Gort Reaver he's an engineer, works at a radio company, and he actually read that engineering journal, and he started on his own doing research. And he actually built in his backyard in Chicago this telescope that you see here. So I am flabbergasted by this, because there must have been no homeowners associations. But he was the first one to actually start doing actual astronomy with it, even though he's an amateur. And like I say, that's the telescope he did. So here's his raw data, which he meticulously did, and here's the first sky maps, which he took the raw data and converted it into these hand-drawn sky maps. So, as I was saying before, when Lord Kelvin and Nikola Tesla were looking at radio, or from the way away from the sun, they couldn't see them. And why is that? Because the atmosphere affects our ability to see, and we sort of take it for granted as optical astronomers that we can just look up and see the sky. Well, that's because now my pointer is gone, but there's a if you look at the visible light portion over here, so this is opacity is on the left-hand side and frequency on the x-axis here. And the visible light, there's an open window. We can see that. But if you go higher than that, the atmosphere protects us from ultraviolets and X-rays and gamma rays, thankfully, because we'd be cooked if it wasn't. And then if you go down the other side into microwave, you can see that there's a window there, and it blocks it clear down till you get to radio waves. And then there's a block, and then there's a big window at radio waves until you get down here to about 3 megahertz or lower, and then you're back to block again. And that's where Lord Kelvin and Tesla were looking. So the window here is from about 3 megahertz up to about 380 gigahertz, and it's free looking at the sky. Okay, so when you look at the universe through different frequencies, well, different things are going on. And this is one of my favorite slides, because you see what the universe looks like at different frequencies, and that's a representation of different things that are going on. When you look at the optical one here, you can see that there's a lot of black in that. Well, why is that? It's because dust blocks much of our view of the sky. And particularly at radio frequencies, you can see right through dust, which is very convenient when you're trying to look at things, you're not blocked. So what are we actually looking at? Well, we're looking at space. And, it's important that we recognize that, because, it's not like regular radio. We're looking at space. So it's the detection of photons at frequency below light. What it's not is Jodie Foster listening to Little Green Men on there. No radio astronomer ever sits there with headphones on and this quizzical look on her face, with the exception of Jupiter, which I'll show you in a minute. But there's no modulation of the signal. And I'll talk a little bit more about that here in a bit. You're just looking at the pure raw signal strength. And so there's lots of objects that are out there, and things like supernova emit strongly in radio. Radio galaxies, there are 2 colliding galaxies, also emit strongly. And so those 2 things are very powerful in the sky. And the signal strength also depends on frequency. And as we'll see in just a minute, that there's a reason for that. And here's an example of what you can see. So the image there on the left here is a very large array looking at the Sagittarius A. So this is the center of our galaxy. So optically, if you go down and look at that, as the summer sky, you look down, you see here's the Milky Way, and as it hits the horizon, you see it bulge out. Well, that's the center bulge of our galaxy, but dust clouds block our view. So when you're looking in with the radio telescope, here you're looking in, and you can see it's lit up pretty strong. And if you look inside the little square here and you go over, and here's a slightly different but zoomed in frequency, well, that's lit up even more. And then if you go and look at the subsection of that, now you begin to see structure in the inner galaxy. And if you go even and zoom in on that, there's even more structure. But what's important is that little white dot right there. And that little white dot is the event horizon for the supermassive black hole that's at the center of our galaxy. So if you're taking, there's millions of stars in the center of our galaxy, and there's hydrogen on them, the supermassive black hole is pulling that off of there. And as it pulls it off and sucks it in, it has to collapse. And as it collapses, it compresses. And it compresses up to 170,000 degrees Kelvin. And as we'll see in just a second, that's a very strong radio emitter. And then right before it goes across the event horizon, you're getting a strong emission because it's at 170,000 degrees Kelvin. And this is the kind of stuff that radio gives you. And so if you, obviously beautiful pictures by Hubble and the James Webb Telescope, But here's an example of this is a picture from Hubble, and optically it's very beautiful. But when you add in the radio, this came from a very large array, you'll see that out of this galaxy here, there's these super powerful jets, which if you were only looking at optical, you wouldn't be able to even know they were there. So when you combine information from different frequencies, you begin to understand what's really going on. And so what has radio astronomy contributed? Well, there's estimates that maybe 2/3 of what we know about the universe comes from radio astronomy. So like what? Well, supermassive black holes and neutron stars, quasars, pulsars are all radio astronomy stuff. The original gravitational lensing was sensed by radio telescopes, and continental drift. I'll show you in a minute how they did that. And you know, who would have guessed that radio telescopes would be able to actually prove, and I have air quotes on the prove, that there's continental drift is an actual real thing. So there's, and I'm just going to just very tiny touch on the physics of this, but there's two categories of things that are radio emissions. One is thermal radiation and the other is non-thermal, and that's synchrotron and spectral line. So I'll just briefly talk about these. So black body radiation, anything that has temperature emits, and we know there's equations that go along with this. And so the higher the temperature, so over here is emitted energy on the y-axis, and the frequency of emissions here on the x. So the hotter things are, the higher the peak. So at 3,000, you see the peaks way down here, 3,000 Kelvin. 4,000 Kelvin goes up, 5,000 Kelvin. So our sun's about 6,000 Kelvin, which is centered right in the yellow. And so it strongly emits at yellow, but also notice that it emits also on the higher frequencies. So this would be ultraviolet, ultraviolet. And then it also emits on the other side. So clear down here in the radio, down here, it's still emitting. Now it's not as strong as it does in visible light. But so a strong emitter is the thermal. And here's a whole chart of a whole bunch of those curves. And so if you go to 170,000 Kelvin, which is the temperature of that the hydrogen as it goes across the event horizon, it's strongly emitting. If you go down here and look, its center peak is ultraviolet. So what that tells you is the center of our galaxy is bathed in ultraviolet light. But if you follow the curve down here, it's still strongly emitting in the radio. And in Sagittarius A is one of the very, very strong. Sagittarius A is what we call supernova, anyway, the big black hole, the supermassive black hole, that's what I'm looking for, is still strongly emitting in the radio. And then spectral, or the synchrotron radiation, any charged particle on a magnetic field will emit. And so there's strong magnetic field lines in supernova, and there's all kinds of charged particles. So those charged particles are spinning around. Well, that spinning around is an acceleration. And so supernova remnants strongly emit synchrotron radiation as a result of this. And then maybe the most important of all is hydrogen atoms have a hydrogen, or a proton and a neutron, proton and electron, and they have something called spin, which is a quantum mechanical thing. And when they're both aligned, it has a certain energy state. Well, on a half-life of about 11 million years, it'll decay from, the electron will decay from a spin up, they call it, to a spin down. And when it does that, it's a lower energy state. It emits a photon at 21 centimeters frequency, or 1420 megahertz frequency, 21 centimeters in wavelength. And this is the strongest emission. There's so much hydrogen in the universe that this is a very important line, and it's right at that exact spectrum. And if it's blue shifted or Doppler shifted because it's coming towards you or away from you, you'll actually see that 1420 megahertz will shift either higher or lower frequency depending on how the movement of that is. And this is very important. So those are the sources. When you look at radio objects, so if you look at optical objects, the brightest objects in the sky are the sun, the moon, Venus, Jupiter, Mars. all of them in our solar system. Then you hit Sirius, which is only 8 light years away, and Saturn back in our solar system. So almost all these things are in our solar system are close. When you look at the radio sky, the brightest object's the sun. Next is that Sagittarius A we were just talking about, the supermassive black hole at the center of our galaxy. And then the galactic plane has a lot of, billions of stars, so it emits strongly. Jupiter at some frequencies, not the ones I look at. So 75 megahertz, it's real strong. Above that, not very. But Cassiopeia A, which is supernova remnant, supernova remnant, is in our galaxy. Cygnus A, which is 2 colliding galaxies 600 million light years away, is the next brightest. So if you can go down the list here, Centaurus A is also a colliding or radio galaxy, and then Taurus A, supernova remnant. Most of those are not in our solar system, of course. So that's interesting. So what does a radio telescope look like? So the one on the left here, this is the Owens Valley 40 meter, which is the Caltech telescope up. Owens Valley is just north of Barstow. And this is a picture I took from Society of Amateur Radio Astronomers, which I'm a member of, has a Western Conference all over the place. So last year it was up here at Caltech's Owens Valley. So that's what that one looks like. This one here is the 110 meter at Green Bank. It's the biggest movable thing in the whole world. And because we have a special relationship with the National Radio Observatory, we get to go and get special things. So I've been right up on this very tip of this thing, which is 470 feet up in the air. The collecting area of this telescope here is 2.3 acres. I mean, it's just a massive collector. So these are obviously big, huge telescopes. But here's a little 1 meter one I'm going to talk about in just a minute, which is amazing to do amazing things in Dr. Thornton's yard. And then here's the very large array, which is 27, 25 meter telescopes. And you see that in the movies and stuff. And as I showed you some stuff from there earlier on. So what are some characteristics of signals that radio picks up? Well, these signals are weak. And so there's a saying that a strong signal is a cell phone on the moon. And I'd heard that for a long time, but didn't necessarily believe until I actually did the calculations. And sure enough, so with the telescopes that we're talking about, even as amateurs, the fact that you can pick up a cell phone on the moon with all the other noise around is pretty amazing. And speaking of noise, there's lots of it. So there's just noise because of all the electrical and stuff that's going on around us. There's heat stuff all over. There's just an amazing amount. And so it's not easy to do, trivially easy, but it's amazing that we can do what we do, particularly as amateurs. And then, so what are the parts of a typical radio telescope? So you need to have an antenna, you need to have a preamp. Why is that? Because those signals are so weak, you have to immediately amplify them. Otherwise, they won't even be able to make it down the coax cable. And then it goes to some kind of a receiver, and then it goes to a recorder. And that's basically that. So what a total power telescope does is it just looks at and says, what's the amount of energy I'm receiving? Remember, there's no modulation. There's no signal on it. So if you were to put a set of speakers on the receiver, a strong radio signal would sound like a loud hiss, and a weak radio signal or no radio signal at all would be like a low hiss. So that's really not more complicated than that. And so why even do amateur radio astronomy? Well, it's relatively inexpensive, and I'm going to show you some things here in just a minute that are with a few $100. And my C8 cost a whole lot more than that, right? So relatively inexpensive. One nice thing is it can be done day or night. And when I first got started in radio astronomy, that was kind of a weird thing to get used to, because I was used to planning that, M1 or M5 or whatever it is, is going to set at certain times. So I had to plan here, I'm going to look at this then, and you have to really be careful about night and day, and you have to worry about whether the moon's out or if there's clouds. Clouds don't affect radio astronomy. It's the same night and day. You can do real science, and I'll give you some examples of that in a minute. You're able to look at, be able to enhance your understanding of the universe by looking at other electromagnetic spectrums. And because of the way you have to take data and analyze it, it's actually, I feel like, easier to see what is actually happening instead of just seeing it. So all those things make, I think, for a good reason to even look at it. This is an actual radio sky image. Now, the bottom part's superimposed. It's the telescope that actually took it. But everything above that, so if you had radio eyes, you could see that's what a radio sky looks like day or night. And so it's the fact that you can do things in the day. It's, works just as well in the day as at night. So I'm going to take a little whirlwind tour here on several different radio telescopes that any one of us here can get. And so you can see that the costs range from about $89 or less up, to maybe $650 at the high end. So we're just going to take a whirlwind tour through here. So the first one is the scope in the box. And I really can't emphasize how cool this is enough. So I told you I'm a member of the Society of Amateur Radio Astronomers. For several years, I was on the board of directors. So it's the biggest group of amateur radio astronomers in the world. And I was on the board of directors of that for several years. And in those days, frankly, most of the members were professional electronic engineers and ham radio guys. And so the nerd factor was off the charts. And they would rather build all the kind of stuff themselves. And my background is physics. And the last thing in the world I wanted to do is go design a filter or something, electronic filter. So what I wanted to do, and which was the emphasis of my work on the board, was to give us a system that an 8th grade science teacher could just go plug in just by connecting just simple connectors, and you'd be able to do real cool science. This is it. And so this scope in a box is exactly that. So one of the things about it is you're going to actually be able to create an image of the Milky Way through the dust for $350. And so let me just briefly walk you through that. So the picture down here, this was produced by NASA and JPL, but it's a map of the universe. Now, obviously, no one photographed it, right? But this is a map of the universe. So let me start by saying there's a problem. How do you get to images? So this is a professionally created image, and it looks beautiful, but it started with raw data. And this is exactly what raw data looks like. So this is some of my own data, and you can see there's all kinds of stuff going on in here. You can see that here's the signal, whatever it is I'm looking for. Here's satellite noise pollution. Here's the sun. You can see it coming in. If you go back to the ground, remember the ground emits because it's got a temperature, but I'm hotter than the ground was that day. So here I am. So how do you take these squiggly lines and convert them into a picture? Well, the software that comes along with the scope in a box does that for you. So here's an actual image that Dr. Andrew Thornott in the UK, member of SARA, produced. And so the colored part here is the data he did with this little telescope, and he superimposed it on that image from NASA. And so you can see here's the arms of the galaxy, and the colors here have meaning. So the blue means it's coming towards you, red means, so it's blue shifted, red means it's going away, and yellow's neutral. And then it automatically takes all the data and puts it into an image, and then he, like I say, superimposed it over the galaxy here. And the fact that here's the sun and we're looking in towards the center of the galaxy, this is amazing. You're looking through the dust. And so then you say, well, why isn't the whole picture done here? And that's because he's actually still doing this in real time. So he sent this to me, allowed me to use it. And when he's done, he'll have the whole galaxy here mapped out. And it's just phenomenal. And so anyway, I'm going to buy one. And it's so cool. I can't even believe it. So the fact that you can actually take an image or make an image, map the universe for $350 is amazing.
Where'd you go?
I saw back at Kara.
Oh.
So remember I told you that there's red shift and blue shift. So the fact that it's able to do that, it tells you which part of so you may or may not know this, but even though the galaxy is rotating, different things in it and different arms are moving at different speeds. And so you can actually see which ones are moving towards you and away from you, but also on the arms, depending on where you are, you're getting different speeds. And that image that he produced is able to show that because you're being able to pick up that Doppler shift. And so another thing that he was able to do with that, because you can see the speed of rotation here, he looked at it and he says, well, we know from Kepler that things that are closer to the center of rotation usually have to go faster, and things that are farther away out. That's why Mercury zips around, but Pluto slowly goes around. And so he took the data from this thing and mapped it out, and he was looking to see if you could see basically dark matter. And what he discovered was our galaxy is rotating in such a way that it's non-Keplerian. And the only way you can explain that is because of the presence of dark matter. So next really cheap thing here is the itty bitty. And the itty bitty, as you can just see, is a repurposed satellite dish. And it has a voltage, what's called a voltage controlled oscillator, which means that when it has a strong signal, it has a high pitched sound. When it's a low frequency or hardly any energy less. So you set this up, and it's a good demonstration thing. You can, when you aim it at the cold sky, there's no radio coming from some parts of the sky, so there's not very loud. When you step in front of it, it sees you as a warm body, so it goes higher. So what it shows is that there's differences in electromagnetic frequency, and it says $89 here, but I put this one together for, frankly, scrounge parts for a whole lot less. So anyway, that's just kind of a fun thing, and if we're outreach guys or something, it's a nice attention getter. Okay, this super SID is measuring the effects of the solar mass coronal ejection. So what are those? Magnetic fields on the sun, when they collapse, it hits the sun and it shoots off stuff, solar particles out. And so why do we even care? And it hits the Earth's ionosphere. And that's where we get the aurora that we saw a couple days ago. But why do we care? Well, if you're outside of the Van Allen radiation belts, for example, astronauts going to the moon, their lives are at risk, and those things could kill them. Also, satellites that are far out are at risk, and even the particles that get through the Van Allen radiation belts can get picked up by the power grid or pipelines and cause all kinds of problems. So this little simple system here, which is $125, you just take this, plug it into this very simple antenna here, and the signal is coming from the Navy needs to talk to submarines underwater, and it does that by broadcasting at really low frequencies, so 24,000 hertz, so really low, and it's got a 2 million watt transmitter up in Washington State. And so all this thing does is it looks at that signal. We don't care what they're saying. It just looks at what that signal is. And the signal has to bounce off the ionosphere. And so during the night, it's a very good reflector. And then during the day, it's less, unless it gets charged up by these coronal mass ejections. So you can actually see them. And now I didn't have mine up I just moved a couple months ago. I haven't reset it back up again. But it would have been nice to see what was going on here with the aurora, and you can actually track all this, and it's kind of cool. Okay, Stanford has all these thousands of these out throughout the world, including in third world countries. They're only $125. They actually give them away to third world countries, and the antennas are so easy to make. You just there's a wire they provide, and you can just wrap it around, as you can see in that simple arrangement, and then you hook that thing up to the internet, and it sends back to Stanford. So you're actually part of this is a real ionospheric research thing run by Stanford that you're actually part of, and so you're actually doing real science with this. And the good part is you can just set it up and let it run, and go back and look at it, look at the data from everybody else, and anyway, it's pretty cool. Okay, this is amazingly cool. So this is called the Naval Observatory. It's a 20-meter telescope in the National Radio Observatory at Green Bank. And this is the telescope that So there's this telescope in Green Bank, there's another one in Germany. And so they tracked together an object, and by using a process called interferometry, they were able to see that the continents were drifting apart. The continents move at the speed that your fingernails grow. And so the fact that these things, by using interferometry, were able to tell that the continents were actually drifting apart, actually prove it, is an amazing thing. So as a member of SARA, if you have a $20 a year membership to Society of Amateur Radio Astronomers, and with a little bit of training online, very easy, you can have access to this. And so in last month, we had the solar eclipse. Here's some radio images of the solar eclipse, and you can see it getting smaller and smaller as the sun was blocked. Now, notice that in West Virginia, it was not a total eclipse. That's why it doesn't go down. But, you know, that's kind of cool. But I'm going to show you Cassiopeia. So remember that supernova remnant. Here's a picture that James Webb took of it in last December. So this is the optical image. So 2 days ago, I went on there and I did a scan. And here's what the scan, you can see it goes back and forth and down a little bit. So it's just a raster scan back and forth. And here, you know, here's the data. So it shows you the frequency spectrum, and you can see whether it's redshifted or not, but I'm just showing that. But here's the image it created. So this is an image I created off of this thing just 2 days ago, and I'm going to compare it. So here on the right-hand side is the image of it done by the Very Large Array. So when I did it on the 20 meter here, first off, it's a smaller telescope, but I only did 6 minutes worth of scanning. When the professionals did it, the Very Large Array, they did it for hours and hours and hours and hours. But even my little simple one here, look, you can see the structure, you can see all this in here. And you know, there's lots of actual real science you can do here. This program is actually run by University of North Carolina, and they have on the website lots of science that you can do through interaction with this. So this is available to, you know, to anyone who wants to join SARA for $20 can do that. Now, I have another telescope, which is a 608 to 611 megahertz one, and this is data that I took at different elevations, and I created. So on the left is me using the 20 meter. On the right is a basically sky map of that other data I just showed there. So you can see that it's actually quite a bit more sophisticated. The stuff on the right is kind of primitive, and if someone was a way better Python programmer than I, you'd get a way better picture on the right than I was able to create sort of simplistically on there. But I also, that same night, I looked at globular clusters. So, you know, as everyone knows, globular clusters are several 100,000 to maybe millions of stars. This is M56. It's not the most spectacular by a long shot, but it happened to be up when I was doing this. So this is the Hubble Space Telescope picture of it. And so I thought, well, I'm kind of curious to see what that looks like in radio. So once again, I did my same scan as the last time. Here's its spectrum, a little bit different. I won't go into the deep differences, but if you really cared, you could look. And here's the image. Well, notice this image looks like crap. Well, why is that? The reason is because not everything is a good radio emitter. And so globular clusters are terrible radio emitters. So the optical picture is great. The radio picture, no one cares other than to see. So I just wanted to point out that, you know, whereas we saw the radio jets on that one galaxy, that was really cool. Here's an example of radio producing dud. So nothing, but anyway, here's something called Radio Joe for 384. So you put up some antennas around your place, you hook it into that little black box, which hooks up to your computer. And so Jupiter produces radio. Why? Because it's got a strong magnetic field, and it's interacting with all kinds of other particles. So like Io throws off particles, and it produces sound. And so here, if you can track that, when the comet, I can't remember the name, the comet crashed into Jupiter, you know, that produced all kinds of things. You can actually hear all this stuff. And I'm going to show you here on a website you can look at. So if you go look at this guy's website, he's actually got sounds, and there's these little very rapid clicks, it sounds like, there's a process that's going along with that. There's others that have longer, that kind of goes ooh, ooh. So both of those are mechanisms that are going on with Jupiter. And there's, surprising to me anyway, surprisingly large number of people that are really hugely into this. And anyway, you can do that for relatively inexpensively. So here's another thing. So these magnetometry is the study of the Earth's magnetic fields and how it interacts with things. So one of the things that it affects the Earth's magnetic field is these solar wind or coronal mass ejections, that sort of thing. And also things on the Earth, like earthquakes and maybe volcano. And so you can actually measure these. And how do you do this? Well, you take these sensors, like what's shown here in the center, you bury them in the ground, and then this one happens to be radio connected over here to this device. And you can actually measure all this. And if you have a couple of them around, you get three-dimensional. And so you can actually track that. And then finally, this is my 608 to 611 megahertz telescope. And so we were at a conference, and Shad Nygren said, why are we building everything ourselves when the industry has spent millions of dollars developing stuff? Why don't we freeload off of that? And so I was looking for a project, so I said, okay, fine. So the antenna here is a Radio Shack UHF antenna. 608 to 611 here is channel 37, which is right exactly squarely in the middle. So it's optimized for that, and it's a protected, channel 37 is protected. So here's a Radio Shack antenna. I hooked it up to a Channel Master preamp, because remember the signals are weak. Hooked it through a ham radio receiver. Nowadays, you go through software-defined radio, even easier than this. Goes through your computer, which is running software, and does output. So remember when I showed those squiggly lines and stuff, all of that was recorded on this little simple system. So buying all these things, including the computer, came up to about $600. And so, and by the way, this is a surprisingly powerful telescope here. And there's a picture of the antenna in my backyard, and just set up and let it drift across as the Earth rotates. So now, in conclusion, I just want to take just a couple minutes to talk about the special interest group that we're trying to form here in radio astronomy. So it has three focuses. One is the outreach program, and I'll talk more about these just briefly in just a minute. Second area of focus is additional options for San Diego Astronomy Association members, which are personal tools that maybe we do as a group, and then that 20-meter telescope. And I put in here mentoring. And I found that this is really important to be able to have success here. And when I first got started, thankfully, I had good mentors. And sometimes you just have questions that then when you find the answer, you go, I'm an idiot. And it's nice to be able to have someone that can just say, oh, you missed something here, just go do this or that. And so you want people to be successful. And so mentoring is a huge part. And then research, we have some opportunity to actually do real research. So as far as the outreach, the idea is to provide additional tools like that itty bitty, or like maybe this, and I'll talk just a minute about a 2 to 3 meter telescope radio dish out at Tierra del Sol or something like that, and curriculum, so that they could actually go and supplement their existing outreach efforts, which I'm super impressed with, super good job. And so provide these tools, and these tools then they could be used also during the day. And just interestingly, and this is a little bit anecdotal, but actually there's been a little bit of research on this. This whole area of radio astronomy is an area that has been particularly attractive to particularly young girls. And we know that young girls are interested in science, and then something happens about middle school years where they fall away from it. And for whatever reason, like I say, there's actually been some studies on this. This is the kind of thing that is attractive to them. So it's a way to keep young girls and young women interested in science. And so we could probably help with that in our local area here. And then as far as the additional astronomy options, there's all those personal ones, like I mentioned. By the way, there's others I didn't include in there. We could also link together stuff. So I'm going to get some of those magnetometers put in my yard and, maybe put that up on the site. Others could do as well, and we could sort of compare data. I'd like to put a 2 to 3 meter steerable telescope out at Tierra del Sol. And so even though it's only 2 to 3 meters, not 20 meters, there's still a lot of really cool and interesting stuff you could do both individually and as part of either an outreach program or some real science. And then, of course, there's, as I pointed out, we can have access to the 20-meter naval telescope. And then finally, there's research stuff. So some of these tools that I already talked about here already could be used to do real research. If you had a 2 to 3 meter one, there's some projects that you can do, and particularly the way that the atmosphere affects your viewing and that sort of thing. And I have in mind a proposal to do a legitimate research grade telescope with multiple, basically it's multiple antennas that would be stuck in corners all around the Tierra del Sol, so it wouldn't interfere with anything else. And in talking with, and I had an opportunity to talk with the grant distributor at National Science Foundation, and it appears that there's an opportunity to even maybe get some NSF money for that. So anyway, all of these things would be remotely operated, so you wouldn't have to necessarily be on site, taking into consideration the limitations on power and that sort of thing that Tierra del Sol has. It may very well be that we'd have to power all this stuff with solar panels. But anyway, that's the presentation. Are there any questions?
That was a lot of good information, Curt. If members are interested, who do they contact to get more information? There you go.
You can contact me. I forgot the last slide.
Skit. So, perfect timing.
Yeah, so if you're interested, so basically what qualifies you to be interested? Just have an interest. So you don't necessarily have to have any particular skill, and you don't have to be a programmer, you don't have to do any of that. Just have to be interested in it. And like I say, we're trying to put together a group of like-minded people and interested people. And if you're interested in any of the things that I talked about, we can help you get set up with that. And there's more, which I didn't get into just because I didn't want to overkill. But yeah, just let me know. I'm sure we'll be sending out some more information to a wider group. But for now, if you're interested, just contact me and let me know what you're interested in if you have a particular topic, or just that you're interested in general. So that's
Thanks,
it.
Curt. That was a really good. A lot of information to absorb. Thank you so much. And if anybody's interested, check out the email. Take a note.
I have just a general question for you, Curt. I'm trying to wrap my head around imaging using, radio waves. I sort of understand. So in one of those, it looked like you said you created a scan pattern. So you're literally pointing this telescope that has some sort of like focal length, I guess, aperture. I'm trying to translate it to terms that I already just barely understand. And you're essentially pinging an area of the sky to see, or listening to an area of the sky to see how much signal is there at a specific frequency.
Yeah.
And then you're moving it sort of a little bit to the right, down, left, down, right, down. Yep. And then you're using that data to generate essentially a heat map.
Right. Well, each time that you're looking at something, so mm-hmm. I take a reading.
Yeah.
Think of that as a pixel.
Yeah.
And so there's a certain strength of that. And if I color coded it a certain thing, to represent signal strength, and then I went to the next one. So when you look with your eye, of course, you get lots of pixels all at once. Or if you do a camera, it looks like, you're actually doing them. But that's what it is. Now, in order to get those beautiful pictures, there's a lot of signal processing going on with it too. But at the very simple level, it's each time I sample, that's a pixel. So it's one pixel at a time.
Yeah.
So when it's doing that scanning, it's pixel, 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 pixel.
Yeah. I guess the optical equivalent is you're taking a photodiode, a single photodiode, pointing it at a section of the sky and saying, is it bright or not? And how bright is it?
Yeah. So when if you think about the chip on your
it's millions.
Camera, well, there's millions and it reads them, but believe it or not, it reads them one at a time, right?
Mm-hmm.
So even though it's there at once, when you actually take the data off, it's picking them off one. Now you don't see that because it happens so fast, but yeah. Anyway, hopefully that helps understand.
That does, yeah. Okay, that's fascinating. So for the one where you were doing a scan, is that mounted on like a is that mounted on on an equatorial mount, or how are you doing a scan like that?
That 20 meter is actually
that was on that big telescope you showed the picture of.
Yeah. That's me remotely accessing. So if I could, I could set you up, Francisco, and you could go and scan that yourself or whatever thing you wanted to look at. And by the way, I just showed you a couple things there.
Sure.
There's a lot of other stuff you could do, and I didn't have time to get into it, but.
So one last question, sort of a la Hubble palette, right? Where we're using sort of different filters on the visible spectrum. I guess that's not, on the light spectrum, and then assigning sort of color values to that. Does something similar exist in radio astronomy, where you're looking at different frequencies and then sort of overlaying all of that data in one single map?
So every radio image that you see is a false image, right? Because and so what happened is somebody had, usually it's signal strength. Now it could be, I'm not going to get too far into this, but sometimes you look at either phase or I'm blanking the word here, but anyway, other factors of the signal that you might, but almost always it's signal strength. Okay. And so you say, this particular one, we're going to color red if it's low and blue if it's high. Okay. And so when you see those, for example, remember I showed the one picture of Cassiopeia A that the pros did, and it was kind of blue and all that stuff. Yeah. Well, each one of those colors represented a particular, were assigned that color to represent a place on whatever the spectrum they were looking at. Okay. And you can begin to see the detail, but every one of those is a false picture. Yeah, I was just so that technique is what they use to generate things like that. Exactly. That's really cool. Okay. And that one picture, the scope in the box, where he's doing, that's the exact same thing it did too. So it's looking at the signal, so total signal strength, but it's also looking at blue and red shift. And it took all of that. And then all of the data all together and created that image. I mean, the fact that it could create that image, that software by itself is worth $350 to them. And by the way, that little 1 meter dish that or little 1 meter thing here, you don't have to hook it up to that. If you happen to have a 20 meter sitting around, you could hook it up, or whatever that you happen to have, you could hook that up and just that much better antenna gives you that much better signal. And you're just hooking it up to the cool software and the thing that it's actually, the hardware is what's called a dongle. It's just a little thing you plug into your computer, and it's, maybe a couple inch wide by maybe 4 inches long. And that's the hardware. Is it just an SDR? Is that what comes with the telescope in a box, or the scope in a box? The SDR is software defined radio, is actually built into the software. And so you basically, you need to have an antenna, you need to have the hardware, which is that dongle, and then it just by USB-C plugs into your computer, and then the software itself that takes care of everything else. Cool. Yeah, any antenna, the software in a box comes with that 1 meter one, but once you got some experience, you could hook it up to any antenna. He hooked it up. Cool. I saw him demonstrate it to show you how ridiculous it is. He literally took a can, and a can like soup can, and put a pickup on it, which is just a little piece of wire. Yep. And he was able to image the universe. Yeah. Now, it's not that great of an antenna, so you didn't get as good a picture, but he was just showing that, you could do it. So
Yeah, I've definitely made antennas out of Pringle cans before for Wi-Fi. So I'm familiar with the concept of using trash for something amazing.
well, for this, use something better than Pringle can, but you could do it. Yeah.
Very cool. You guys, any other questions for Curt before we move on to the quiz?
One quick question here, B. Curt, through your presentation, you showed demonstrations of data that looked like graphical images. Some data looked more like flux as a function of time.
Yeah.
And another portion looked like flux as a function of wavelength.
Yeah.
So these are separate processes, all using basic radio astronomy techniques. Is that true, or are they combined in some way?
So if you're going to do frequency, you have to have a way to be able to do that. And without getting too much into it, the way they typically do it is you take the signal and you can either deconstruct it using fast Fourier transform, which is a mathematical process for being able to figure out what the frequency is, or you can have separate receivers at all kinds of different frequencies. So the very large array, for example, so I've actually been on site and seen that. There's a room, it's enormous room, that has these basically computers sitting there, and each one of them is maybe a megahertz wide, maybe not even that big, and it's taking the signal and it's just processing that, so that there's literally thousands of little bins, each one a tiny fraction of a frequency apart, and it's being able to take that, so then you get the spectrum out of that. And so for some things you care a lot about that. So if you want to get Doppler shift, you need to be able to see where the signal is compared to the neutral hydrogen. For some things, total power, like the one I put in my backyard that I showed you, the telescope in the backyard, it would be nice to have spectrum on that. But for that one, all I really care about is total power. So my signal width, literally I'm picking up from 608 to 611. So what is that, 3 megahertz wide? And so that's that's a pretty big window, but I'm just looking for what's the total power of the signal that I'm receiving in that window. So sometimes I care about signal strength, sometimes I care about frequency, sometimes I care about, not me, but the radio astronomy community cares about phase. Sometimes it cares about orientation, whether it's polarized. That polarized is the word I was spacing on before. Whether it's left or right polarized, or that kind of thing. So and stuff like the 20 meter, you get to choose all kinds of different things. And for time purposes, I didn't want to get into that. But when you go to the screen to pick what you want, it's not an overwhelmingly confusing option of things you can pick, but you can pick things that are relevant to what you want to find out. And, they've got the hardware and the software there to be able to get you what you need for that. So did that answer the question, Dave?
I think so, yeah. So for the amateur getting into this thing, probably the most interesting thing may be to be looking at integrated flux as a function of time, depending on the antenna you're using, something along that line.
Yeah, well, if I was just starting out, I would go right for that scope in a box. I mean, that's, to me, that was the thing I was aiming for when I was on the board of directors there, and they even took it a step further. I mean, I'm gobsmacked by what they're able to do with that, and the price is only $350. And you can. This, by the way, Reaver put that huge thing in his backyard in Chicago. I showed up, I showed you earlier, and I'm surprised the neighbors didn't run him out with pitchforks. Well, you put these little antennas, even your spouse won't mind that in your backyard. It doesn't take up such space that it's not an eyesore, and so the fact that you're producing that. So I would do that if you have an interest in kind of playing with that 80 or the 20 meter. let me know. And there's some amazingly cool, I just barely touched on what it could do, but, so, if it was me, I would do scoping, but that's why I led with that one. It's such a powerful tool.
Excellent. Thanks, Curt. I appreciate it. Great presentation.
Yeah, thank you.
Hey, I have a quick question if I can.
Yeah, sure.
My name is Sonny. Does it take much of a laptop to work this, or does it have to be like a new laptop, or an old laptop, or does it have to be a pretty powerful laptop? I have a couple more questions after you answer that.
No, and so the software, it's a specialized. So the software I use, a lot of guys use, is if you're not doing the scope in the box, is something called the Radio Eyes software, and basically all it's doing is it takes your sample and it aligns it with, so you tell it where you are in time of day, and it puts it in the sky map, which is an important detail. I mean, you could do it on your own, but it would be a pain. And it's not very strenuous. And if you're, so when the 80 meter's doing, it's actually actively scanning. Most of what radio astronomers do is you set up, you aim south with your antenna, and then you have a certain declination that you're going up, and you just let it go. And as the Earth rotates around, it's called drift scanning. And then you sample, depending on what your beam width is, maybe once a minute or something. So what do you get? 1400 or 1440, I think it is, minutes in a day, something like that. And as it scans around you, so there's 1440 pixels, we're talking about with Francisco. And so it's not very strenuous on your computer. That's the long and short of it. And so probably you could do it with an old computer. I was doing it, so now I have a newer computer, but when I first started back in the day, there wasn't, back in the day computers, early 2000s, were nowhere near what they are now, and it was running just fine. So I think you'd be fine, Sonny.
Is there something that could be done in a short amount of time? I'm thinking like for outreach star parties or something at a school or something like that. Is there something that can be set up and show some data, show a little something what's happening, like with the solar flares or something, in a short amount of time, or does it take longer than for 2 hours?
You've hit, so the thing that got me interested in radio astronomy in the very first place was, so I used to be a very active member of the Salt Lake Astronomical Society. So I was getting my bachelor's degree at University of Utah. And so you go to a star party and, ooh and ah. And when I first became aware of radio astronomy, it's like, oh, this is pretty cool. And my naive idea was, couldn't you just set up something, let it run for the course of a star party, so a couple of hours, and then it would produce, here's your sky map. Wouldn't that be nice? And when I first started doing that, it turned out that's actually, at the time, would have been technologically challenging. Right now, it's not. And that's actually on my list, Sonny, of things to do, is I actually have it was donated to me, an actual controller. It's the kind that the TV stations, when they go and do a remote, actually control those big antennas that they use to signal back. I have one of those. And if you took that, put an antenna on it, controlled it, and you could go to either a star party or an outreach thing, set it up outside, start your thing, let it scan, and while it's scanning, it's processing. And by the time you're done with your outreach, or by the time you're done with the star party, boom, it's up. So that's actually one of the things that I would like, people want to collaborate with me on for the RASIG, the Radio Astronomy Special Interest Group, is to do exactly that. And so I should have probably mentioned that before, but yeah, that's my dream. And we're now at the point where you can actually do it.
Oh, good. All right. Sounds good. Thank you.
Yeah, sure. Sarah has its Western Conference every few years at the Very Large Array. And because we have a special relationship, you can go out there. And I've actually been walking on the dish, one of those dishes. They let you go actually up on there. So
whoa. I was just there a couple days before the solar eclipse as part of the road trip.
That was cool,
yeah, it was a bucket list thing for me to actually go there. But it is sort of restricted the things that you can see and do. That would be
So
amazing.
Francisco, you need to come with me the next time we go out there, and I'll
Let's
take
go.
we get the behind the scenes.
I'd love
awesome
that.
Cool. Awesome cool.
Thank you so much, everybody.
Thanks all. Have a great evening.
Thanks for the great meeting, B.
Thank you, Ken, as always. Thank you, Dave Wood, for running the
Thank you,
slides.
Dee. Thank you, Kurt.
Thanks, everybody. Thanks,
Ready.
Kurt.
Thank
Thanks,
you.
Kurt.
Have a good one.
Bye, everybody.